Hello and welcome back to another lecture on advanced plasticity of solid continua. As you know, this is an NPTEL online course. Today we will be discussing on the rate independent plasticity through the lens of convex analysis. So in the last couple of lectures we already covered some introductory aspects of convex analysis. So it is essential that you need to recall a few of these as we go along in this lecture. So let us first discuss about the potential function, which plays a very important role in defining an optimization problem whose solution will give you the plasticity or the plastic response of solids. So therefore the potential function is essentially like energy, okay, like the free energy in thermoelasticity or strain energy in elasticity. Typically it is a function of the plastic strain rate and other hardening variables, right. We have already discussed hardening. So this hardening could be in the form of kinematic hardening or isotropic hardening. So these variables will also enter the arguments of the potential function phi, right. So the argument of the potential function phi, we are calling it by the name J. It contains all of these, this plastic strain rate being one and the hardening variables. And this constitutes the starting point to define an unconstrained convex optimization problem for plasticity. So it's quite an interesting thing in its own right, because if you define an unconstrained optimization problem for plasticity, then just by solving that unconstrained optimization problem by many different means which are available in the literature, because there is a lot of work done on optimization problems in the literature, right. You can actually solve very accurately problems in plasticity, right. So this is quite a different point of view from the way that typically plasticity is taught from a classical perspective based on a clutter of rules. We have been discussing some of those clutter of rules for some time, right. So this is a different route which is more organized, more principled and more mathematically grounded, more elegant also. So let us discuss about what phi j should be. One thing about phi j, phi is the dissipation potential, phi j is that it is positive and it is one homogeneous. It is Euler one homogeneous function. It is a scalar valued function because it is energy like. So therefore for any positive scalar lambda, correct, phi of lambda j has to be equal to lambda times phi j, right. This is the definition of one homogeneity. Right. So and it has to be positive. Then let us talk about the Legendre-Fenchel dual phi star, right. What is the dual? It is, you know, if phi is in terms of the kinematic quantities like this plastic strain rate, the hardening variables, which are also related basically to the plastic strain rate. You already know that. We have been discussing about it in one of the lectures. But the phi star, the dual, depends on the force like quantities or stress like quantities, like the stress, the deviatoric stress being the main thing on which this phi star, the dual, will depend, right. So we claimed in the last lecture that phi is an indicator function, okay. Phi is an indicator function, but let us prove it now. So let us recall the basic definition of the Legendre-Fenchel transform, right. So phi star works on stress like quantities. Let us call this as x, okay. So remember that x is in the dual space to the vector or function space in which j is, okay. Phi is a function of j, phi star is a function of x. Phi star is dual to phi and x is dual to j, alright. So, the definition of phi star according to the Legendre-Fenchel dual is supremum over all j, admissible j, such that supremum of this x inner product with j minus phi j, right. Now, let us define first, forget about the supremum part to begin with. Let us first define the function h of j equals this argument of the supremum, that is x inner product with j minus phi j, right. Now, you can easily see that hj is also one homogeneous, that is h lambda x is equal to lambda hx for all lambda greater than 0, just as phi j is one homogeneous, hj is also one homogeneous. Now, let us say that we have found some j0, okay. Let us say some plastic strain rate and the hardening variables, call it by j0, such that h of j0 is greater than 0, okay, alright. So, then by the one homogeneity of the function h, I can choose a very large scalar value lambda such that h of lambda j0 should be equal to lambda of h j0, but that should go to infinity if I choose sufficiently high value of lambda. So, in this particular case, this means that the supremum of this h of j, because that is what the idea is, no, the supremum's argument was h of j, okay. So, if h of j goes to a very large value, then its supremum over all possible choices of j should be equal to infinity. So, therefore, we get in this case phi star x equal to infinity, right. On the other hand, let us also talk of the other possibility in which h of j0 is less than equal to 0, then what happens? So, let us consider now h of j less than equal to 0 for all j, okay. So, in this particular case, since h of j is less than equal to 0 and you take a look at the expression for h of j, which is it is given here, this is the expression for h of j. So, we already know that phi of 0 is 0 by the property of the one homogeneous convex function, right. So, phi of 0 is 0, if j I take as 0, then x inner product j is also 0, therefore, h of j at 0 equal to 0. So, that is the maximum possible value that it can have if hj is less than equal to 0 for all of j, right. So, therefore, the supremum in this case must be equal to 0, therefore, phi star x equal to 0, therefore, for all x in this particular case when hj is less than equal to 0. So, in other words, what we are getting as the property of phi star is that phi star is an indicator function, okay, 0 in the domain, call that set K, where hj is less than equal to 0, alright, and elsewhere, okay, it is infinity. So, phi star is an indicator function in this sense. Remember that the indicator function that we use in other applications is often not in terms of 0 and infinity, it is often over the set of interest, it is 1, and outside that set it is 0. That is how we typically define indicator function in other branches of applied science and maths. But in this particular case, we are defining the indicator function in a slightly different way, because we want phi star to act like energy, right. So, energy does not have this 1 0 typical structure, but 0 infinity structure. So, 0 is the minimum of this conjugate energy phi star, and infinity is an extremely high energy which cannot, in which nothing can live, right, because such high energies are practically impossible. Okay, so you also observe one very interesting thing, that is for hj less than equal to 0, this is very important. This hj, which is x in a product with j minus phi j, is less than equal to 0, but phi 0 is equal to 0, I know that. So, 0 I can write as minus phi 0, correct. If I now combine these two, we get, now remove that minus and put it this side, or put that phi 0 this side. So, you can write phi 0 is I will just write phi j, correct. I will write phi 0 this side. So, just rewrite this quantity, phi j is greater than or equal to phi 0 plus x j. This I can write as j minus 0. So, essentially what you see here is that this Hj less than 0 can be written in this manner, but this is nothing but the definition of the subdifferential. If you recall the definition of the subdifferential of phi at j equal to 0, correct. So, that is a very important point, that is, if Hx is less than or equal to 0, right, Hj is less than or equal to 0, then we may say that phi star x is equal to 0 for all x which are in the set defined by the subdifferential of phi at 0, correct. So, subdifferential is the generalization of the notion of gradient, remember that, right. So, this is a very interesting thing. I have explained it. If you find it difficult, then go through this slide and the lecture, this part of the lecture again and again, you will also understand it fully, okay. So, let us understand what it means for plasticity, right. So, phi j, as I have already said, is a dissipation potential, energy like quantity over the thermodynamic fluxes, which is j. J equal to 0 means no plastic flow, okay. That is, the plastic strain rate is 0, etc. Now, phi star x is like the conjugate energy over the thermodynamic forces. These thermodynamic forces are conjugate to thermodynamic fluxes, in the sense that you take the inner product of these thermodynamic forces with the thermodynamic fluxes, and you get, something like the power or energy, or work per unit time, things like that, okay. So, these thermodynamic forces we call by x. Basically, this is sigma 0, the deviatoric part of the stress for nearly incompressible plasticity. So, phi star x is infinity outside the set C, means that the set C of stresses means for all the kind of strain rates and the thermodynamic fluxes for which H of j is less than or equal to 0, remember. This means that C is an energetically, if the stresses are outside C, then the corresponding phi star x is infinity. That means those kind of stresses or thermodynamic forces are energetically impossible. They will never occur. On the other hand, for the kind of stresses for which phi star x is equal to 0, when x is within C, this is the minimum of the conjugate energy phi star. So, all stresses x in C will be permissible, you see. So, we have something like this, a bowl like thing. This is 0, phi star is 0 here, infinity here, right. You can think of this as, the locations, these and these are the locations where the plasticity just starts, and this line, these vertical lines where just phi star starts becoming infinity from 0, that transition happens, this is the boundary of the yield set, okay, the boundary of C. Okay, so we can say therefore that all stresses x in C are permissible. So, C is the set of permissible stresses. The boundary of C, we call it by del C, is the yield surface, right. Now, you see a typical visual representation of this here. So, I can only show you the representation in a 2D plane, because more than that is not possible. You have to imagine in higher dimension. So, phi j is given by this tent like or inverted tent like function, and you can see that if you take the derivative of phi j, subdifferential in general, because when the derivative exists, subdifferential and derivative of the same thing. Along this line, if you take this, you get -1 or minus sigma y maybe here, okay, right. On this line, if you take the derivative or the subdifferential, we get +1 or plus sigma y, the plus of the yield stress, right. On this point, if you take the derivative, you will get so many. This will be one possible subdifferential, you know, this will be another, this will be another, so many you will be getting, right. Okay, so these are the permissible stresses, because as soon as you are taking the derivative of this function phi, you are getting stress like quantity. If you take the derivative of the function phi star, you will be getting strain rate like quantity. Okay. So, this we have discussed in the last class. Then just recall your elasticity and the Coleman-Knoll procedure, in which by taking the derivative of the free energy we get stress, right. With respect to strain, if I take the derivative of the strain energy or the free energy, we get strain, right. So, similar. So, you see that it is at this point 0 of J. When J is 0, that means when the plastic strain rate is 0, the corresponding stresses could be, you know, thermodynamic forces could be too many, This lie, all these stresses lie in the set C. These are this is the set of permissible stresses, okay. So, this has to be remembered. So, you see how we are exploiting the fact that there is a lack of continuity in the derivative information of phi j at j equal to 0, because through that information comes the yield set, right. Now, let us now talk about the Fenchel equality and the maximum dissipation principle. People talk about the maximum dissipation, right. What is it? That the plastic flow occurs, or the plastic stresses are developed, that means sigma 0, the deviatoric stress during the plastic flow develops in such a way as to maximize the plastic dissipation. That need not be a hypothesis here, right. That actually follows from the Fenchel-Young inequality or equality, right. So, recall the Fenchel-Young, let us call it for convenience Fenchel inequality. This is the Fenchel inequality. That means the inner product of thermodynamic force and the thermodynamic flux is less than equal to the dissipation potential phi j plus the conjugate potential phi star x, right. This we have already seen, we have proved it. But we have also proved that when, for example, for a given j, for a given thermodynamic flux, when x belongs to the subdifferential of phi, right, then it becomes equal, this inequality becomes equal. Now, when it becomes equal, then for all phi star, right, for which we are having a finite number, that means for phi star x belonging to C, right, which is actually equal to 0 only, because the other number that is possible is not a number at all, it is infinity, right, outside C. So, therefore, this term goes off. What we are left with is that if x belongs to the subdifferential of phi, is then we are left with the inner product of x and j gives you the dissipation potential itself, and that is the maximum value possible for the inner product of x and j given a j. That means the stresses, the thermodynamic stresses or the thermodynamic forces take on such values and directions as to maximize the work per unit time x inner product j, and that becomes equal to the dissipation potential. That is the maximum dissipation principle. In other words, x in the subdifferential set of phi is the correct stress to work with, right. So, So that corresponds to the actual occurring of the plastic flow, right. So basically this is an important thing, that this makes very transparent the notion of maximum plastic dissipation and this is called the maximum dissipation principle, right. In fact, the physicists have looked at it in a slightly different way. That means maximum dissipation principle also corresponds to the maximization of the entropy. That means given all the non-understanding of the unknowns, right, non-understanding of us by the for the unknowns we don't know, right, their distribution or their arrangements should be such that the possible number of such arrangements will be maximal, right. The uncertainties whatever are there has to be maximized in some sense. This is basically the maximum dissipation principle. This is consistent with this maximum entropy principle, okay. Anyway, so we can actually have another representation of this maximum dissipation principle. It is simply this. Earlier we fixed J, that is the thermodynamic fluxes. Now what we can do, we can fix the thermodynamic the forces, right. For that thermodynamic force sigma 0, let us find J such that that is maximized. The work done or the power input, plastic power sigma 0 inner product with J is maximized. You remember that here sigma 0 is nothing but this x, the thermodynamic forces that we were talking about. So basically from the convex analysis, the dual to the statement of Fenchel inequality is the following. So when it turns out that J is in the subdifferential of phi star at sigma 0, given sigma 0 on the yield surface, then again I can apply Fenchel equality to say that sigma 0 inner product of J will be equal to phi J. Earlier we said sigma 0 belongs to the subdifferential of phi. Now we are saying J belongs to the subdifferential of phi star. In other words, we are now differentiating or subdifferentiating phi star with respect to sigma 0 to get J. Earlier we subdifferentiated phi with respect to J to get sigma 0. You see, so both the ways you can come and get the same principle, and that is a very interesting thing. So both ways it is true. So there is one interesting thing here, I hope you know that, but I will still tell you. Suppose fx, x is a vector, let us say, right. So fx equal to 0 is the equation for the surface, right. F is a scalar valued function, is the equation for the surface, right. So then how is grad of fx directed? We know that grad of fx is I can write, so this is my surface, right. So let us say this is my surface, this is a point x0 on the surface. So fx0 is 0 on the surface, right. So I can actually go to another nearby point x from x0, let us say x0 is 0, okay. Then what should I say, f0 is 0, then I can say that f0 which is 0 plus grad f at let us say 0 dot x dot, this x minus 0 dot will be therefore equal to 0, because that is the increment, this increment, right. This increment, it will give you the increment remaining within the within that surface fx equal to 0, right. So therefore we see from here that x dot is a vector, grad f is a vector, they are orthogonal to each other because their dot product is 0, right. So therefore grad f is always normal to the surface at any point, right. The same principle is valid here, because grad f is nothing but the subdifferential if they are the same, if the function is sufficiently smooth, right. So basically the fact that sigma 0 belongs to the subdifferential of phi is a normality condition, right. Similarly, j belonging to del phi star is a normality condition, correct. So, I can say therefore, j is normal to the yield surface if the latter, that is the yield surface, is smooth enough. Of course, for non-smooth yield surfaces, it actually gives more information, right. It is called the normal cone. I can come to that a little later, because whenever there is a point of non-smoothness, the subdifferential becomes a non-trivial set. It consists of more than one element, and all those elements are valid values corresponding to the plastic deformation. So, therefore, we get a generalization of the normality condition. We have to define a normal cone. The normal cone in this particular case for plasticity is defined for any sigma 0 on the yield surface as NC sigma 0. If that is a point, that sigma 0 on the yield surface is a point of discontinuity or non-smoothness, then del phi star of sigma 0 is a set, that set is the normal cone, right. I will give you more intuitive and image based description of this later on. So, basically what we are getting is that the normal cone basically is a subdifferential of phi star. So, by the definition of subdifferential, I can therefore say that the normal cone consists of all the fluxes j for which, given the sigma 0, j inner product with any other sigma 0 dash belonging to the admissible stress set C, sigma 0 dash minus sigma 0 inner product with j must be less than equal to 0, correct. That is the definition of the subdifferential at basically sigma 0, right, for phi star. So, therefore, basically this is this set of all these possible values, elements of the subdifferential. So, both the perspectives, looking from j belonging to del phi star of sigma 0 or this sigma 0 belonging to del phi of j, they are equivalent. Okay. So, this is exactly what we have been doing. I have told some of these parts of the slides already. So, let us see, in these set of admissible stresses, phi star x equal to 0. So, del phi star is automatically 0 there, right. So, that means that j equal to 0, that means the plastic strain rate within the admissible set of admissible stresses in the interior of C is 0. But del phi star therefore represents a set of plastic strain rates, or more generally thermodynamic fluxes. Within C there are no fluxes, 0 fluxes. For x on the boundary, if the thermodynamic force is on del C, then del phi star x must be the outward normal, because it is a gradient like object, right, with undetermined magnitude, because phi star suddenly changes value from 0 to infinity, correct. So, this is what is important, the normality rule, right. The set del phi star, the conjugate, the dual to phi for x on the yield surface is called the normal cone at x. Okay. So, this normal cone consists of only one element if everything is smooth, the yield surface is smooth. So, we now come to an important concept of the support function that will take for me a little bit of time to explain. So, we will do one thing, we will take a short breather at this stage and then we will come back to the next lecture and continue with the notion of the support function, and see in that lecture that the dissipation potential is nothing but the support function for rate independent plasticity. In other words, based on the notion of a support function, I have a principled means of finding out the dissipation potential. We will talk about it after a breather. Thank you very much for your attention.